So far, Shamir secret sharing gave us a very strong guarantee. So any T participants can recover the secret, and any T minus one or fewer participants learn nothing. But let's talk about how we measure efficiency here. So the first metric is called share size. And so this means the amount of information each participant has to store. And so in Shamir secret sharing, each share is the same size as the secret. So if the secret was one element of ZP, then each participant is storing one element of ZP also. Another metric that is used many times is something called information rate. And so that is the size of secrets divided by the size of all the shares, right? So the rate measures how much real secret information we get compared to the total amount of storage. So for Shamir, if we share one field using n shares, then the secret has size 1 and the total storage has size n. So the rate is 1 over n. And so this may look inefficient because we are storing n field elements in a total to share one field element only, right? But for perfect secrecy, Shamir's threshold actually is the optimal. You can't do better than that for perfect secrecy. So if we want to improve the rate, we need to relax something. And that leads us to something called ramp secret sharing. So what is ramp secret sharing? So a ramp scheme relaxes the threshold secret sharing conditions. So in Shamir's Tn threshold, there is one sharp threshold, right? Any T participants can decode, and any T minus one or fewer learn nothing. So that's the sharp threshold. In a ramp scheme, you have two thresholds instead. So the parameters are T, R, and N, with R in between. And so the idea is that any R participants can decode. So this is the threshold, let's say, for decoding. And any T minus one or fewer learn nothing. So if the number of participants are in between T minus one in between T and R minus one shares, then they may learn partial information. So it's like there is a middle region, and so small groups learn nothing, large groups recover everything, and sort of groups in the middle here, they may learn, so in between, in the middle, right here, they may learn something, but not necessarily the whole secret. And so the benefit is that we can pack a larger secret into a single share. And so ramp secret sharing trades some possible partial leakage in the middle range for better storage efficiency, right? So it's in order to increase the efficiency. So let's look at how this type of scheme looks like. So let's write the general ramp scheme. So the number of secret elements is going to be given. So when you have a TRN scheme, the number of secret elements is going to be given by R minus T plus 1. So you can think of it as instead of storing one secret, you're storing L secrets. And of course, they're all going to be elements in ZP. And once again, you're going to have this thing about P being larger than N because you need to have enough evaluation points, right? Okay. So the first guarantee is that any R participants can decode the entire secret. So that's what we need, right? We need any R participants to decode the secret. And so this is called decodability. And the security guarantee, so called secrecy, is that any T minus one or fewer participants should learn nothing. And the idea is quite similar to Shamir secret sharing. The idea is that you also generate these random numbers. So since you want to protect against T minus one participants, like fewer, you do from R1 to RT minus 1, chosen uniformly at random. And now you define the polynomial. So remember that Shamir was just using the coefficient, the constant coefficient to put the secret. Now actually you define the polynomial where the coefficients, you distribute the secret, so this S1, S2, SL, in the first L coefficients. So coefficient 0, coefficient 1, up to L minus 1. And then the rest of the coefficients is going to be these random entries here, okay? And of course, this is going to be degree R minus 1, because then if you have R evaluations, which is what you want, you're able to retrieve the whole polynomial, and you can then actually solve for each one of these coefficients here. And as before, each participant is going to receive a distinct and non-zero point in ZP, and that's the reason for these points to exist. That's why you need P to be larger than N. So very similar to Shamir, but just adding more coefficients here for the secret. And so let's look at an example. So suppose that the secrets are S1 and S2 in Z5. And so let's build a T equal to 3, R equal to 4, N equal to 4 scheme. So we're going to have 4 participants. We want 4 of them, only 4 of them to be able to decode. And we want less than 3. So any 2 of them will learn nothing. 3 will be allowed to learn a little bit, but you're actually going to need all 4 to be able to decode. So how does this work? So like we said, you build a polynomial of degree R minus 1, so degree 3. You need to have T minus 1 random guys, so these go here. And the secret, you put them in the first coefficients over here. And now you send the 4 distinct evaluations. So we send f of 1, f of 2, f of 3, and f of 4 to each participant. And so f of 1 is going to get this equation here, f of 2 will get this equation here, f of 3 will get this equation, and f of 4 will get this equation. And once again, you'll have a linear algebra way of looking at it. In this case, if you get 4 equations, notice that you have 4 unknowns here, so you can solve for them, and then once you solve for them, you retrieve the secret that you're interested in. So how does that look like? So if you write these out in equation form, so this is going to correspond to the first row, right? So the first row here is S1 plus S2 plus R1 plus R2. So that's this first row over here. The second row is S1 plus 2 S2 plus 4 R1 plus 3 R2, which is exactly this equation here. And so this will correspond to the third row, and this will correspond to the fourth row. And so this is what you get, and what you want is to solve for S1 and S2. Now, again, this matrix here is a Vandermonde matrix, which means that it's invertible, which means that if you invert it and multiply on both sides by the inverse, you'll be able to solve what you want. So that's exactly what you do. You go and you invert, and you can compute this. So you can do Gaussian elimination. Remember that you're working in Z5. So every operation you do, so you need to do the stuff that you learn in linear algebra, but you need to do them over Z5. And so if you compute the inverse of this matrix, it'll be this. And so this will give you the equation. So notice the first row gives you the equation on how to retrieve the first secret. So it's 4f1, 4f2, 4f3, 4f4. And the second row gives you the equations for recovering the second secret. 4f1, 2f2, 3f3, 1f2. And so with this, you're able to get all the secrets. So this is an example of a ramp scheme with parameters 3, 4, and 4. Now, how does this compare to Shamir, right? So in Shamir TN, threshold secret sharing, we share a single secret, and each participant receives 1 share. So if there are n participants, the information rate we saw is 1 over n. Now, in the ramp secret sharing, we're doing multiple secrets, and we are able to improve the rate, right? Now, the trade-off is the secrecy leakage. So in Shamir, you have like a very strong security that is very sharp. So it goes from no one knows anything to now they know everything. Whereas here, it goes from no one knows anything, then in between here, they can start to learn a little bit, and then after, they know everything. And so with that, ramp secret sharing is able to give better efficiency, but by allowing partial leakage in the middle range.